Well, hello everyone, welcome back to my channel, and this video is the continuation of shear and torsional resistance of a pre-stress concrete member, where I will be discussing a problem regarding this topic. So let's read the problem statement. A post-tensioned bonded pre-stress concrete beam of rectangular cross section 400 mm wide and 550 mm deep is subjected to a service load bending moment of 166.6 kN meter, torsional moment of 46.6 kN meter, and shear force of 66.6 kN. The section has an effective pre-stressing force determined from service load requirement of magnitude 500 kN at an eccentricity of 150 mm, provided by 5 numbers of 12.5 mm stress relieved strands of cross-sectional area 506 mm square with an ultimate tensile strength of 1820 Newton per millimeter square. If the cube strength of concrete is 40 Newton per millimeter square, design suitable longitudinal and transverse reinforcement in the beam using IS 1343 1980 code recommendation based on skew bending approach. Well, we will be conducting this problem today based on the skew bending approach only. We will not be adopting this Prestress analogy. So these are the given data where the ultimate bending moment, ultimate torsional moment, ultimate shear force, these all are calculated with multiplying 1.5 factored load. So we have considered the factored load while designing this. So ultimate bending moment M equal to 1.5 into the value in the question which was given, and the product is 250 kN meter. The ultimate torsional moment 1.5 into 46.6, and the ultimate shear force is 1.5 into 66.6. The area of pre-stressing strand is given in the question. The ultimate tensile strength of a strand is also given. Cube strength mean FCK is given. Yield strength of transverse reinforcement is 250 Newton per millimeter square. This has been assumed. Pre-stressing force is 500 kN, eccentricity 150, width of the section 400, overall depth capital D 550. The area of a concrete section is 22 into 10 to the power 4. Well, this is the product of multiplication of B into capital D, which is 400 into 550. The second moment of area I will be B D cube by 12. The effective stress in steel will be P by A, area. This area is this area of pre-stressing strand, and 500 kN, this is the pre-stressing force per area. We have got the effective stress in steel. The effective depth small d is 425. So how did we get this value 425? It is capital D by 2, which is 550 by 2 minus the eccentricity. It is minus the eccentricity. So this will be 125 millimeter. So actually the cross section, if we draw this, the B is 400, the capital D is 550, the eccentricity, the neutral axis will pass from the center of the section. So this will be the half of 550, which will be 275 millimeter. And in question it is given that a magnitude 500 kilonewton at an eccentricity of 150. So the eccentricity, let's consider this 150 distance from the neutral axis, 150 millimeter. So the rest, so here 5 numbers, 1, 2, 3, 4, 5. So the rest of the distance remaining will be 125. So 550 minus 125 will be our 425 millimeter. Okay. So now adopting the skew bending approach, which is given in IS 1343/1980, we will design the longitudinal reinforcement and the design of transverse reinforcement. So let us discuss the design of longitudinal reinforcement. This is provided in the clause 22.5.3.1, where in the code it is described that the ultimate bending moment, which is ME1 equal to M plus MT. So what is here MT? MT is denoted as capital T root over 1 plus 2 capital D by B. So this is the bending moment which provides the torsional effect at the cross section of the beam. So we will calculate this MT, we will put the value of T which is provided, and we have also multiplied this factored load as a 70 kilonewton meter. So we will put this value 1 plus 2 into capital D 550 millimeter divided by B 400. So we got this MT, mean the bending moment due to the torsional effect. So it is 136 kilonewton meter, and the moment, this is the ultimate bending moment M, which we have calculated as 250 kilonewton meter. So summing this two moment 250 plus 136, we are getting 386 kilonewton meter. So this is the ultimate bending moment ME1. So we will design this section by considering this ultimate moment. So the ultimate moment capacity of 386 kilonewton meter, this value will give me the assumption of determining the balance moment or the section we have to choose for the pre-stressing steel. So for the pre-stressed section, we have already got this values from the question, where FP is 1820 Newton per millimeter square, where FP is the ultimate tensile strength of strand, AP is the area of pre-stressing steel, FCK is the cube strength of concrete, B and small d mean the effective depth. So by considering all these values, we will calculate this ratio. So this ratio is also called, or can be also called as, an effective reinforcement ratio. So considering these values, we will get the value of this ratio. So here, after calculating, we have got the ratio to be 0.135. So from IS 1343 1980, from table 11 we will get the value corresponding to this 0.135. We will get FPU divided by 0.87 FP to be 1, where FP we have to calculate the FPU. We know FP, which is the ultimate tensile strength of strands. So multiplying this factor with this, we will get FPU. So FPU is 1583 Newton per millimeter square, where FPU is the ultimate tensile stress in the tendon. Now from this ratio we also got XU by D to be 0.287. So we know small d 425. So XU is 122 millimeter. The unit is here, it is wrong. So this will be the moment of resistance of the section. So putting all the values, we will get the moment of resistance of the section to be 299 kilonewton meter. But the total moment to be resisted by the section is 386 kilonewton meter. So here what will be the balance moment? So the balance moment will be 386 minus 299. So actually up to this, the calculation of moment was only due to the cross sectional area, the effective tensile strength of a steel. We have not considered the torsional effect in this calculation, but by cooperating the torsional moment into account, we have got this moment. So we have to consider this moment to be the final. I mean, by benchmarking this moment we have to design. So this 299 kilonewton meter is the only moment resistance of the section without incorporating the torsional effect. But we have to consider this because this moment is incorporated with the moment resistance of a section plus the torsional effect coming onto the section. So the balancing moment will be 87 kilonewton meter. So now we can calculate the reinforcement to be provided for the longitude as a longitudinal arrangement. So here from this formula we can get the value of AST, mean the longitudinal reinforcement the required longitudinal reinforcement for this section, where mu will be this balance moment, because this moment we have to resist, because this excess of moment we have to resist. This excess of moment should be resisted by that longitudinal reinforcement. So that moment should be taken into account, and by putting all the corresponding values we will get the value of AST. So 840 millimeter square, so providing 2 bars of 25 millimeter dia each at effective depth of, here it will effective depth of 500 millimeter. So AST, the actual AST, provided AST will be 982 millimeter square. So by considering the pre-stressing effect, the torsional effect, we have achieved the longitudinal reinforcement requirement to be the provided AST will be 982 millimeter square. Now we will design the transverse reinforcement. So in order to calculate the ultimate shear resistance of an uncracked section in a flexure, we need to know the value of Ft, means the tensile strength of concrete, which is 0.24 root over FCK, which is provided in IS 1343 1980 clause number 22.4.1. So we will put the value, and we got 1.51 Newton per millimeter square. Now in the code it has been prescribed that the torsional moment and shear carried by the concrete can be measured by this expression, where this represents Tc1 equal to capital T C within bracket small e divided by small e plus small e subscript c, where this Tc representing this expression, where actually there will be a summation, where this expression here it is given 0.15 b square capital D 1 minus b by 30 into lambda p root over FCK. These are given in the clause 22.5.4.1. Here we have to calculate all the values. In order to calculate a value in an expression, we need to solve the another expression. So it is a longer procedure to solve it. So in here, in order to get this expression, we need to solve Tc. In order to solve this Tc, we need to solve this lambda p. So here lambda p is given as whole root over 1 plus 12 FCP divided by FCK, where FCP is the average intensity of prestress at the centroid. So what is the average intensity of a prestress at centroid mean? Due to that prestressing effect, what is the average intensity coming into the centroid of the beam? So this is the force of the prestressing steel, and this is the cross sectional area. So actually this is FCP. So 12 FCP divided by FCK. So putting this value, we are getting lambda p as 1.296. Now this Tc was 0.15 into b square. So here b is 400 into capital D. Capital D here is 550 into 1 minus small b divided by 3 into capital D into lambda p 1.296 root over FCK 40. So after calculating this, we are getting 82 kilonewton meter. Now we got this Tc in this expression. Now we have to evaluate this small e and small e subscript c. So now this small e expression is given as capital T by V, and small ec is provided as capital Tc by capital Vc. Here what is the meaning of T, what is the difference between capital T and Tc? Here capital T is representing the torsional moment applied to the cross section under ultimate load conditions, and this Tc representing the torsional moment carried by the concrete. So as same with the V and Vc, just the difference, this is the torsional effect and this is the shear force effect. So from here we know capital V and capital T to be 70 and 100 kilonewton. So in order to calculate this TC by VC, we need to evaluate this two terminology. Now, what is this two terminology? This is VCO and this is VCR, where VCO is representing the ultimate shear resistance of a section uncracked in flexure, and VCR is representing the ultimate shear resistance of a section cracked in a flexure. In here, this VCR should not be less than the 0.1 BD root over FCK. Now, this VCO is represented as 0.67 small b capital D root over FT square plus 0.8 FCP FT. This expression is given in the clause 22.4.1. So putting all the corresponding values here, where Ft square is 1.51, here the Ft we had calculated, and this 0.8 FCP, this FCP is 2.27 Newton per millimeter square into Ft. So we have got the value of 330 kilonewton. Now we will calculate this VCR. So in order to calculate this VCR, we need to know that this M naught. So in order to calculate this M naught, we need to go to this expression where it is given M naught is equal to 0.8 FPT into 1 by Y. So here this FPT is represented as the stress due to the prestress only at depth small d and distance y from the centroid of the concrete section. So this is the normal formula of PT. So providing this value where P is 500 kilonewton, A is 400 into 550, P into eccentricity was given as 150, and Y is here also 150 divided by the second moment of area. So 5.54 mean that BD cube by 12 formula. So this is the value, and we have got PT to be 6 Newton per millimeter square. So here we have got FPT. So after putting this value 0.8 into FPT, so putting this value, we have got M naught to be 69.23. So now we have got this M naught. Now we will calculate this tau C. So in order to get the tau C value, we need to go for this ratio where 100, it is given as 100 area of pre-stressing tendon divided by BD. So here AP will be actually the equivalent area of pre-stressing steel is obtained. Actually in this case the pre-stressing steel is provided to be, this is 506 millimeter square which was given in the question, and AUS actually here we have already calculated that provided longitudinal reinforcement into that Fy divided by Fp. So the ratio of this tensile strength of strand and the yield strength of transverse reinforcement multiplying by that longitudinal reinforcement provided reinforcement we have given, we will, by adding with this 506 millimeter square, we will get the equivalent area of pre-stressing steel for this case, for this section. So this AP is 635 millimeter square. So putting this value, we are getting this ratio 0.373. So from this ratio, we will directly go to the IS code and verify the table 6, where for M40 grade concrete, the design shear strength tau C will be 0.44 Newton per millimeter square. It is given in a tabular form. It is provided in table 6, where in corresponding to this ratio, M30, M35, M40 grade of concrete's shear strength is given accordingly. So after just doing the interpolation, we will get the tau c to be 0.44 Newton per millimeter square. Now putting all the corresponding values, 1 minus 0.55 FPE. What is FPE? It is the effective pre-stress after all losses have occurred. So we have already calculated this earlier as 988 Newton per millimeter square. So this is the value divided by the FP, which was given as 1820 Newton per millimeter square, into here tau c is 0.44 into B 400 into small d 425 plus m naught. We have calculated it is to be 69.23 into 10 to the power 6 divided by that capital M. So that capital M is this ultimate bending moment 250 kilonewton meter. So after calculating all this, so we will get this VCR to be 80.1 kilonewton. So the smaller values of VCO and VCR obtained to be this 80.1 kilonewton. So the minimum from this 330 and 80, the minimum value is 80.1 kilonewton. So we will go for this value. So here small e was equal to capital T by V. So we have calculated this earlier in this section as well. And now that small EC equal to, this will be capital TC divided by capital VC. So here this TC is, we have calculated this in this portion, 82 kilonewton meter. So this is 82 and VC we have calculated to be 80.1. So E subscript C we have got 1.02 meter. Now we will calculate TC1 and VC1 as this equation. So TC1 we have got capital TC to be 82 into small e 700 divided by 700 plus this EC 1020. This TC1 we have calculated to be 33.37 kilonewton meter and VC1 is 80.1, this VC1 into 700 divided by 700. So this ratio will remain the same. So this VC1 will be 13.02 kilonewton meter. So this formula is given in the clause 22.5.4.2. So after calculating this value, we will calculate the design of transverse reinforcement. So now we will calculate this, and this formula is given in the clause 22.5.4.3, where this is the design of transverse reinforcement, where the area of cross section A is V. This A is V of a closed stirrup enclosing the corner longitudinal bar shall be taken as the larger of the following two values. So here, after looking at the expression, we need to evaluate this. So here A is V, this is represented as M1 SV divided by 1.5 B1 D1 Fy. So here M1 we have already calculated it here. So this is M1, we have calculated this as 136 kilonewton meter. This was the ultimate bending moment. So 136 kilonewton meter into 80 is the spacing of the stirrup reinforcement divided by 1.5. B is, this is 350. This is 350 because we have considered this as to be the center to center distance between corner bars in the direction of the width, and D1 to be 450 because we have also considered it as from center to center distance between corners bars in the direction of the depth. into Fy. So this ASV comes to be 184, and AV, here AV is represented as V minus VC1 into SV divided by 0.87 FYD1. So this V minus VC1, we have calculated it earlier. V here, this is the V 100 kilonewton, and this VC1 is 32.59. So here we already calculated this 32.59. So subtracting this, we will get 67.41 kilonewton into SV divided by 0.87 into Fy into D1. Again, for AT, it is also given as expression of capital T minus capital TC1 into SV divided by 0.87 B1 D1 Fy. So here the T minus capital T minus TC1, so capital T, it was given in here 70 kilonewton meter, and the TC we have calculated here by this expression 33.37. So after putting all the values, corresponding values, we have got this corresponding areas. So this ASV is calculated as equal to AV plus 2 into A capital T. So this is for shear, this is for torsion. So we have got 225 millimeters square. So the larger value among all this is 225 millimeters square. So we have designed as per this area. So we have provided 12 millimeter dia, 2 leg stirrups at a spacing of 80 millimeter, which we have considered here as SV, which provides also ASV to be 226 millimeter square. The whole design procedure which I have elaborated, I hope you have understood it. Thank you for watching this video.